An empirical formula is a chemical formula that gives the smallest whole number ratio of atoms in a compound. As an example, let's take the molecule ethene, which has 2 carbons and 4 hydrogens, so the molecular formula is C2H4. But notice that both subscripts are divisible by 2. So, to figure out the empirical formula for ethene, we have to find the smallest whole number ratio that describes the relative number of different atoms. So, we divide both the 2 and the 4 by 2 to get the empirical formula CH2. If we want to get the molecular formula from the empirical formula, we need to do the opposite of this. We would multiply all of the subscripts by 2. This is because, for ethene, the empirical formula is different than the molecular formula. For an unknown compound, we would need to determine the common factor of the subscripts, 2 in the case of ethene, using an experimental technique such as mass spectrometry. Sometimes, the empirical formula and the molecular formula are the same. A common example is water, which is H2O. That means that there are 2 hydrogens for every 1 oxygen. Now, let's suppose we have a mystery compound that's 84.1% carbon and 15.9% hydrogen, and we want to figure out the empirical formula for our mystery compound. A useful trick is to assume that we start with exactly 100 grams of the mystery compound. That means we have 84.1 grams of carbon and 15.9 grams of hydrogen. Our first step is to convert the masses into moles. We can look up the molar masses for carbon and hydrogen on the periodic table. The molar mass of carbon is 12.0 grams per mole, and the molar mass of hydrogen is 1.01 grams per mole. We take 84.1 grams of carbon and divide it by 12.0 grams per mole. The grams cancel out in the division, and after we divide the numbers, we're left with around 7 moles of carbon. We next take 15.9 grams of hydrogen and divide this number by 1.01 grams per mole. This tells us that we have 15.7 moles of hydrogen. We now have the relative number of moles of carbon and hydrogen in our unknown sample. We next try to divide all of our numbers by the smallest number in order to figure out the ratio of these 2 elements in our sample. So we divide 7 moles of carbon by 7 moles to get 1.0, and we divide 15.7 moles of hydrogen by 7 moles to get 2.24. At this point, we might be tempted to write that the empirical formula of our unknown compound is C1H2.24, but the empirical formula has to have whole numbers as the subscripts. So we need to figure out the smallest whole number to multiply all of our subscripts by so that all of them are whole numbers. 2.24 times 2 is 4.48, which is not a whole number. 2.24 times 3 is 6.72, which is still not very close to a whole number. But 2.24 times 4 is 8.96, which is extremely close to a whole number, 9. So we multiply both of our subscripts by 4 in order to produce the empirical formula C4H9, which is the smallest whole number ratio of different elements in our sample. Now, let's say we use a mass spectrometer which tells us the molar mass of the mystery compound is 114 grams per mole. Next, we need to use the empirical formula to find the molecular formula. We start by figuring out the total molar mass of our empirical formula. There are 4 carbons, each with a mass of 12 grams per mole, and 9 hydrogens, each with a mass of 1 gram per mole. So, the molar mass of our empirical formula is 4 times 12 grams per mole plus 9 times 1 gram per mole, which is 57 grams per mole. If we take the molar mass reported by the mass spectrometer and divide it by the total molar mass of our empirical formula, that's 114 grams per mole divided by 57 grams per mole, which equals 2. This means that to get the molecular formula, we should multiply every subscript by 2, which gives us the molecular formula CHH18. This molecular formula tells us the true structure of the molecule. C8H18 is a molecule called octane. Drawing out the 8 carbon atoms and 18 hydrogen atoms, we can see how these different atoms covalently bond together to form a molecule. Now, it's also possible to do the reverse, to start with the empirical formula and then calculate the percent composition. As an example, let's calculate the percent of chlorine by mass in 3 separate compounds. The first compound is sodium chloride. Whenever we go from an empirical formula to percent composition, we should assume that we have 1 mole of our compound. So let's assume that we have 1 mole of sodium chloride. If we break it apart, we end up with 1 mole of sodium cations and 1 mole of chloride anions. Sodium has a molar mass of 23.0 grams per mole, and chlorine has a molar mass of 35.5 grams per mole. So the mass of 1 mole of sodium chloride is 23 grams plus 35.5 grams, or 58.5 grams. To figure out the percent of chlorine by mass, we can just divide the 35.5 grams of chlorine by our 58.5 grams of sodium chloride, and then multiply by 100 to get 60.7% chlorine by mass. Doing the same calculation for sodium tells us that sodium chloride is 39.3% sodium by mass. Or, since the total should add to 100%, we could find the 39.3% by subtracting 60.7 from 100%. Now, let's do the same calculation for potassium chloride. 1 mole of potassium chloride gives us 1 mole of potassium cations and 1 mole of chloride anions. Potassium has a molar mass of 39.1 grams per mole, and chlorine has a molar mass of 35.5 grams per mole. Adding these masses together, the total mass of 1 mole of potassium chloride is 74.6 grams. So, once again, we can find the percent composition by dividing each constituent element's mass by the total mass. So, 35.5 divided by 74.6 gives us 0.476. We then multiply by 100 to get a percent composition of 47.6% chlorine. Doing the same calculation for potassium tells us that potassium chloride is 52.4% potassium by mass. 47.6% is much lower than the percent chlorine composition in sodium chloride, which was 60.7%. The difference is the mass of the cation. While both compounds have the same relative number of chloride ions, the sodium and potassium cations have different masses. Potassium has a higher molar mass, leading to a higher mass percentage for potassium and a lower mass percentage for chlorine. Let's do one more calculation for magnesium chloride. Unlike the previous two compounds, magnesium chloride consists of a magnesium 2+ cation which binds with 2 chloride ions to produce an electrically neutral compound. So this time, 1 mole of MgCl2 has 2 moles of chloride anions and 1 mole of magnesium cations. That means that 1 mole of MgCl2 has 71 grams per 2 moles of chloride and 24.3 grams per mole of magnesium. And so, the total mass of 1 mole of MgCl2 is 95.3 grams. Now, if we divide the mass of chlorine by the total mass, which is 71.0 grams divided by 95.3, then we get 0.745. Multiply by 100 to get a percentage. So, magnesium chloride is 74.5% chlorine by mass and 25.5% magnesium by mass. Since we now have 2 chloride ions for every 1 cation, the percentage of chloride ions by mass is larger than the previous two examples. Alright, as a quick recap, empirical formulas tell us the smallest whole number ratio of different types of atoms or ions in a compound. For covalent compounds, empirical formulas may or may not be identical to the molecular formula depending on the actual structure of the molecule. Empirical formulas are helpful in figuring out the chemical structure of unknown compounds when given analysis results showing the percentage composition of the compound. We can also use empirical formulas to compare the mass percentages of elements in different compounds.